binary black holes. And those signals, among a lot of cool science, they enable us to probe directly, or they give us a direct window into the dynamics of the merging black holes and of the Kerr metric in particular. And so many of us have been trying to figure out novel ways to actually leverage these signals to actually learn something about the structure of the spacetime around black holes. So my very, very, very biased opinion is that the most exciting development along those lines over the last few years has been in trying to use the ringing of black holes as represented in the later portions of our signals to actually learn about this structure. So by the end of this talk, I hope I convince you that this is the case. I will argue that ring-dots are quite interesting and promising. I will explain why it's taken us some time to actually take advantage of this kind of study, what the challenges are in implementing these sort of studies in our data, and that will help you understand the measurements that we have been able to do and how those may lead to improved versions moving forward. So to get started and to make sure we're all on the same page, our goal is going to be to try to understand what black holes really are. Are these objects the black holes, the simple objects we expect from Einstein's theory? Do they have horizons? Are there deviations? Could they be mimickers? I don't know. So are these really the objects we think they are? So if you're like me, your first instinct to try to study such an inscrutable object might be to just throw something at it and see what happens. And it turns out that, if this perturbation that you create is big enough, that's not a bad idea. A black hole, like many objects, if you perturb it, will ring in a set of quasi-normal modes that will get translated into a gravitational wave signal of very specific frequencies, an imaginary frequency that has some oscillatory part and some imaginary part that tells you about the decay of these modes. And these modes of gravitational radiation will have certain amplitude and phases that are encoding the nature of the initial perturbation that excited the black hole in the first place. So as I said, this is not uncommon. It happens with many, many objects that you're familiar with. And in fact, I'd like to explain this in analogy with a bell, because it's really the exact same situation. If you have a bell and you strike it, the bell will vibrate and emit sound. It will get rid of that extra energy that you've given it. And it will do so in very specific tones, pitches, and durations that encode the geometry of the bell, the material, the size, etc. While the loudness of the different modes tells you about the kind of excitation, where it happened, and what kind of phenomena gave rise to the excitation in the first place. So by studying these quasi-normal modes in the signal, either the sound for a bell or the gravitational waves for a black hole, we can try to pin these frequencies and extract those from the data and reconstruct part of the geometry of the object. For a black hole, if everything is as we expect, this should mean that we can learn about the mass and the spin and the charge that are the only three properties that should determine everything about a black hole as we expect it to be. In an astrophysical context, the charge is not expected to be relevant, so we usually just talk about the mass and the spin, and we expect this space-time metric of the black hole, the geometry, to be fully described by the Kerr metric describing this geometry. So if this is not true and you need some other new number to describe the space-time of a black hole that is not the mass or the spin, or in theory the charge, then what you're looking at is not a vanilla black hole as we understand it. And this is a result over a statement of the well-known no-hair theorem. Or if you're a mathematician, it's a no-hair conjecture. Let's be careful. So this gives us a unique opportunity to actually experimentally try to check whether this is the case when we have access, if we had access to one of these ringing black hole signals. And that's the program known as black hole spectroscopy, in analogy to the program, or to the long tradition of understanding what atoms are like by studying the spectra of atomic transitions. This is a similar endeavor. And so this fact that the geometry of the spacetime should fully be explained by two numbers allow us to do two things. So first, assuming that fact, you can use the signal of the ringing of a black hole to measure the parameters, the mass and the spin, and learn about the properties of the black hole, assuming it's the object we expect. But you also can enhance your model and try to look for deviations away from that and see if there's some feature of the spectrum that is not explained fully by the mass and the spin as we expected. So is it all right if I take this off a little bit? Is that okay? I'm like drowning. Okay, so to do that, all you need is a signal template model for this ringing, and this will become a little more important later on. And this will be a superposition of a number of quasi-normal modes, as I explained, with some complex frequency that has a real part and an imaginary part that defines the mode. And these frequencies are indexed by L, M, and N. The L and M represent the angular part of this ringing, and they are attached to these spheroidal harmonic functions, the SLMs, that are sort of like the usual spherical harmonics that you know and love, except they account for the oblateness of the Kerr geometry, so they're not spherical. But for all intents and purposes, if the spin is low, it's almost the same. And then for each L and M, there's an infinite ladder of modes indexed by N, which orders these tones by damping time in such a way that a greater N means the tone decays faster and faster by definition. So these are called the any tone with N other than 0 is called an overtone, and it's somewhat of a misnomer. So keep that in mind. Overtones in the rest of physics tends to mean higher frequency. Here it means that the decay is faster. It's in fact the frequencies tend to be a little lower. It's not a multiple of the frequency. Anyhow, so this should describe fully the ring down signal. In fact, if we are doing data analysis and we only care about the frequencies, we can absorb this in here, and this simplifies a little. But anyway, this long story short, this allows us to create a model for the signal LIGO may see, and we can use that to, for example, parameterize the frequencies and damping rates as a function of mass and the spin. They are fully known if you assume the object you're looking at is a Kerr black hole. Or you can introduce additional deviation parameters, some delta F and delta tau, that for any given mass and spin will allow the spectrum to deviate away from what we expect from Kerr. And you can measure M and chi and these deviations and do all sorts of cool science with that, perhaps compared to theories or other models and so on. Of course, we should expect to find deltas to be 0 always if the object we look at is a Kerr black hole. So that's all well and good. It'd be great if we had a black hole sitting there and we could just perturb it in a different way, excite different modes, record with LIGO what the response of this object is and measure these frequencies. But of course, we can't have such a clean experiment. What we do have in real life is a snapshot of this process and by which two black holes in spiral slowly starting from far away, they eventually form a common horizon, merge and form a final black hole that is excited from this violent process that gave it birth, and it radiates away this excitation in terms of these normal modes that I just described. The stages of the process roughly map into the different stages in the signal that LIGO may detect. As you know, these waveforms represent the stretching and the squeezing in the interferometer arms. Early on, in the spiral, this roughly corresponds to the black holes when they're far away. Eventually, they are plunging and merging. And finally, you should end up with something that's fully described by these quasi-normal modes, these damped sinusoids with the frequencies and damping rates, as I explained it. So there's a question exactly as to if we're trying to target this very clean regime where the signal should just be damped sinusoids, where exactly should we look? I mean, clearly it'd be silly to look here. That we do not expect that part of the signal to at all correspond to a single black hole that has been perturbed. If you go very far down at later times, that is probably guaranteed to be vibrations of the final black hole. But the signal decays very quickly, so you don't want to wait too long or the signal will have faded and you can't really extract it at all. So what we want to go as early as we can without contaminating with the previous part of the process. In practice, what we do is define operationally the part of the waveform that is the ring down of the final black hole as the part that is described empirically as a superposition of that sinusoids based on numerical simulations. So we can look at a bunch of numerical simulations and see exactly where at which point the signal starts being described by the spectrum of the remnant black hole, which we know because in the simulation we know what it is, and we can check that. So we can use this in our models. Of course, in reality, everything is trickier because what I was showing you is the ideal signal. In practice, what our detectors might see is a much noisier version of this. And this is actual data for 5914. And so to actually do this kind of measurement, we can't just look at the data and try to measure what the frequencies are and say, oh, they match. We need some sort of more sophisticated analysis strategy to handle that. So in the LIGO Virgo world, there are, roughly speaking, two philosophies for doing this that are complementary in different ways. One way would be to say, well, let's look at the way in which we measure regular parameters for our binary black holes. We have a template model that is this parameters in terms of masses and spins of the initial black holes, and that determines the full waveform, the spiral merger ring down. We can enhance these models with artificial degrees of freedom that allow the waveform to deviate in the later part that could absorb deviations in the quasi-normal modes, and we could try to measure those by analyzing the whole waveform at once. The other strategy is, well, that sounds complicated. Let's just chop the data at some point where we think the ring down starts and look only at data after that and try to fit them sinusoids directly to this and extract frequencies and damper rates. So the first strategy has the advantage that it's actually very straightforward to implement. So this is like, it happens to be easier to fit into the usual framework of LIGO data analysis. And so it's easier to actually do, but it has a disadvantage that by construction, you're coupling your ring down measurement to everything that came before it. And so you're susceptible to systematics in the attachment of the ring down to the merger or possible deviations. If the final remnant is not a Kerr black hole, then probably the earlier part of the signal also is not exactly what we expect it to be for two Kerr black holes. And so your measurement of these deviation parameters will be necessarily tied to the whole thing, and it'll be hard to disentangle. At the same time, so we can introduce similar parameters like I mentioned earlier with these delta S and delta taus, and they will be telling you something about the consistency between the different ring down modes, but also between the ring down and the merger, because you're doing everything at once. So this is one way of doing it, and we, in the collaboration, we have done this. I've been an advocate of the second avenue of the second philosophy of doing this, which is let's just identify a point where we expect the ring down expect the signal to be described by quasi-normal modes of the remnant, cut it and just look at that portion, fit quasi-normal modes, measure the frequencies and check if they agree with the expectation. This happens to be conceptually cleaner, but in practice harder. And so, you never win. And it took us a long time to actually get this right. And I and others were the ones who figured out how to do it around 2018, 2019 or so. It took a while. And the reason, roughly speaking, why it was hard is that usually when you do analysis with LIGO, you're grabbing a whole segment of data, you're Fourier transforming it, and you're doing everything in the Fourier domain. That means you take an FFT, and your signal's in the middle of the segment of data that you're analyzing, and you don't have to worry about windowing or anything because your signal's safely in the center. If you want to have an analysis that just starts abruptly at the edge of your segment, right? Because you want to cut the data and throw everything away before the ring down has started, then you have to deal with issues related to windowing. If you don't do anything, if you try to Fourier transform this thing that you've chopped off the stuff coming before the peak, then you'll get all sorts of artifacts due to the sharp start of the signal. If you can try to smoothly window the signal starting, or the data starting a little before where you think the ring down starts, which here's the dotted line. But in that case, you will contaminate your measurement with a little bit of data before where the ring down was, and so you get some biases. And the same thing, if you start a little later, you'll be throwing away some data that could be potentially be valuable about the ring. So it took us some work, us and others, to rethink the way we do analyses. It doesn't matter the technicalities, but what matters is that this is a reason why we've started doing these ring down measurements in 2018 and not in 2015. And eventually we figured out how to do it in a correct way, quite different from the way we usually do LIGO data analysis. And once we figured that out, we're able to recover a number of damped sinusoids. It doesn't matter what came before the start of this regime of the signal in which it can be described as a ring down, and we can recover and reconstruct the different modes that make up this oscillation. If you don't get this right, you actually get it wrong. So if you're not careful about the treatment of the data, it will be easy to think you found a deviation. So in this case, I'm showing what other people had done before, which was almost right. But if you're not careful about these conditioning issues at the edges and you use the traditional approaches, you'll get a measurement of the frequency and damping rate of a damped sinusoid, in this case, a simulated signal that is off away from the truth. And if you are careful about these things, then you get it right. So
I have a question. Yep. So yeah, I mean, your description of the data analysis part, the challenges is very clear. I'm wondering about the underlying physics. You are assuming a damped sinusoid. That's fine in the linear regime. But if you're cutting early, you have to worry about nonlinear mode coupling and all sorts of stuff. So how do you handle that?
That's the next part of my talk. Perfect. All right.
Great.
So can we actually do this? And there are complications like that. So the traditional expectation was that no, precisely because of what you were saying, right? Like the expectation was that near the peak of the signal, where at the strongest, the waveform should be dominated by nonlinear effects, whatever that is, in the theory. And so you want to stay clear from that and go as late as you can. Of course, if you go late, as I mentioned, that means that you are losing SNR, you're losing signal to noise ratio because the signal decays very fast. And so it becomes a hard challenge. Furthermore, if you want to do this consistency test by which you need several modes, usually if you want to pick more than one mode, people have been thinking of different angular modes. And if you're here, you may have hope of seeing the dominant quadrupolar mode, but the higher harmonics of the angular vibration are way weaker, and it's hopeless down here.
So sorry, I might have missed it early on. In the template library that you already have, right? There you are modeling them continuously, aren't you? Or is that already chopped?
Yeah, so there's like three different ways, three different families of templates that do this in different ways. The traditional templates have some prescription for the ring down that could be in terms of explicitly quasi-normal modes or something similar in
like
the Fourier domain.
Expansion.
Yeah, and then they will, or it could be like a Lorentzian with some exponential in the Fourier domain, and they have some prescription for attaching that to the early part that comes from post-Newtonian theory and calibrations to numerical simulations. And those are the traditional models. Nowadays, we have more modern waveform models that are directly trained on numerical relativity simulations, and they don't have an explicit analytical parametrization of these modes. They're basically machine learned replicas of the NR waveforms directly, and those are way more faithful.
So they are contiguously fitted for all the stages.
Yeah, without okay. It doesn't know anything about quasi-normal modes. It's just replicating that artificially. And those happen to be in the parameter space where we can check way more accurate. They don't have issues of artificially matching and so on. Although even the older models that did the patching have gone way better, and they get better every time.
I wonder if you could comment on the following, which I keep hearing people say, and I ask, and I never really understand the answer. So it's related to Ramesh's question as well. So the people like Thibaut Damour and Alessandro Bonanno, and then they talk a lot to these people who sort of come from theoretical physics, who study amplitudes and so on. And I guess scattering is on here now, but the people in the scattering. And the picture is that they use is that first you have this sort of in spiral incoming phase, and then this in spiral phase, and then bang, they merge, and then you're in the ring down phase. And for some reason, which I don't understand, that what the phase that I think Ramesh was referring to comes and goes before you can blink your eye. Why is that?
Yeah, the answer I think is like no one knows. But that has to do with what I'm going to say in a little bit. But as it happens, the regime where these nonlinearities are important is really the preceding regime is like when the plunge is, it's like the end of the spiral. That whole part is very nonlinear. But then as soon as a common horizon, so we don't know for sure, but current investigations point to a picture in which as soon as a common horizon forms, every nonlinearity that can be around in that space-time doesn't make it out to infinity. So what we see is very quickly the linear regime. So I will come back to
I would
that.
have thought the time scale from that. This is, I'm just re-saying what Ramesh is saying. I would have thought the time scale for that to happen, for the time, the merger, for them to, that time scale would be the same as the quasi-normal, because there is no other time scale in the problem.
Right.
So, but apparently not. Is that right?
That appears to be,
understanding this
but
correctly?
it's at this moment is mostly an empirical finding. There's some people are working very, so I'll come back to this in a little bit. So clearly, so there are nonlinearities
Yeah.
in this whole part before, when the dynamics here are very nonlinear, like just the low PN order, Poissonian orders, that doesn't cut it. And so that's why people compute all these smart ways of pushing the prescription all the way up to as close as they can to a peak using this newer scattering amplitude and
But it's
Feynman
still
diagrams and things.
perturbation theory.
Yeah, and they're pushing it as close as they can. It's perturbation theory, but it's nonlinear.
I thought they were nuts when they kept trying to do this, and then the numerical people started agreeing with them. So
Yeah, so if you look at predictions from Kip back in the 80s or whatever, what he, before NR came along, you know, the drawings for what a waveform looked like used to be like sinusoidal and then like some craziness, and only later on these damn sinusoids. That just happens to not be the case. And so the intuition that seems to be appearing, but I can't, this is not my expertise, but it's what the, well, okay, I'll return to that in 2 slides. Is that okay? Because I have I was planning on talking about that a little bit. Is that fine? All right. Okay, so the expectation was exactly this, that this regime should be highly nonlinear, that you would have to go later on, and if you want quasi-normal modes, multiple quasi-normal modes, if you are looking at different harmonics, the secondary angular harmonics are much weaker than the dominant, and so it's basically hopeless with current detectors. This picture left out the overtones, so they were all, everyone, at least in the data analysis world, most people were thinking of just the fundamental mode of each angular harmonic, for which the previous statement is true. You have to go very late in the waveform, and the other modes are much weaker. But if you look at overtones of a given angular pattern, in particular the dominant angular mode, the quadrupolar 2-2 mode, it turns out that allows you to come way closer to the peak, and they are way louder. And so you no longer need to go down here, and this brings this sort of experiment within reach of current instruments. Now, I'm going to give you a little sidetrack into overtones, and it relates to these sort of questions that you've been very cleverly bringing up. Yeah.
You keep on referring to testing the no-net theorem, and I really have to lodge a small objection here. The no-net theorem really refers to what happens in infinite future time, and you don't actually know what the mass of the black hole will be in infinite future time. There's another merger of violent that happens in the future, and you don't actually know where you're looking as far as the event horizon goes. So I really wouldn't call this a test of the no-net theorem.
Well, except that we think we know what it should be given. So we have the NR simulations that tell us what the final remnant is. So we measure the initial parameters, and we have some measurement, projected measurement of what the final mass should be. But this doesn't.
That's a mass at the end of the particular merger you're looking at. What if there's a shallow lake that's 1 light year in diameter that's surrounding this entire thing,
right,
or around us, in fact, and it's going to collapse into a black hole, and we just have no idea.
So what we're testing is this emission consistent with a Kerr spectrum, and we tend to call that test of no-Kerr theorem, and there might be a bunch of caveats to that. Apologies. the experimenters will. It's good to make that distinction. In practice, we expect that what we get from in our simulations for the final parameters should be infinite enough. We don't know. Maybe that's not true.
But it's only a few orbital times later, right? The simulations don't go on for that long.
Right, but they go on until the signal effectively has died.
Oh, okay.
So I don't know. We can't measure anything else. Right.
Yeah, I concur with that.
It could like
You guys-
spontaneously form something that's not care, but
Right.
we are checking, is this part
Care
of the
come
behavior
back.
of care or not?
Yeah.
And that doesn't, sorry, 1 second, that doesn't require knowledge of the final mass and spin a priori. As
Yeah,
long as
sure.
you have
Yeah, yeah.
two modes, you're just checking whether it's
Yeah,
self-consistent or not.
But I would
Yeah.
not say that's not trust of the known theorem, also not necessarily trust of GR, because GR doesn't tell you the intermediate times it has to be per.
Right, well, there's input from GR in how and where we're looking, and we're basing a lot of this. It's not just of care, it's of the whole evolution. Part of it's influenced by our understanding of the whole binary evolution. So there we go. Yeah.
In addition to all these points, and I hate to throw a spanner in the works here, but the no-head theorems just don't hold when you have Vlasov, for instance, Einstein-Vlasov, which is a really nice model to model astrophysical systems. So I think that's also something interesting to consider. I mean,
I'm not familiar with that. Do you want to say? I'm not sure what that is.
so the theorems, right? So the theorems say the theorems usually work in vacuum.
Yeah.
Sometimes they work when you add a matter field that has particular properties. So for instance, Maxwell's a good example. Maxwell still lives in the class of theorems where you have these kind of uniqueness theorems. Notwithstanding all the issues of regularity, etc., which is what the mathematicians also really care about. But anyway, for non-abelian matter, so Yang-Mills, for instance, or more flat-footedly for Vlasov, just dust, kinetic theory type matter, there's manifestly non-uniqueness. I mean,
Okay, sure.
the existence of solutions that are stationary, but certainly don't have any kind of uniqueness.
Okay. Yeah. No, that's fine. I will just ask you for the remainder of this talk and for when we know her theorem, it's doing it's just absorbing a lot of assumptions that are not just what purists like you from my point of view. No, like fairly so. But like it's fair, it's totally correct to make these distinctions. We're assuming it's a binary black hole merger in vacuum. We're assuming all these things that are all part of the assumptions that we're testing, if you wish. It's added to and that's all packeted for us in our lingo. Apologies, in what we call the no-hair theorem. Fairly, maybe we should find a new, more generic word to say. But all these tests that we do in LIGO, tests of GR, it's not a test of GR, it's also a test of, we're assuming there's no eccentricity, we're assuming all these things, right? And we tend to clarify that in the papers if we remember. If not, you should call us. But yeah. So keep that in mind. That's fantastic. I should have totally been clear about formally what we're testing. For my purposes, I'm checking whether the spectrum is a curved spectrum or not. And then if it's not, we'll go back and check which of all these things could have broken and explained it more likely the noise in the instrument. So if that okay, so forgive me, with apologies for my sloppiness. I'll move on. And so part of the story that matters for the empirical act of measuring is these overtones play a big role in the kind of measurements we have done. Some of you may remember Matt Giesler gave a talk here several years ago about right after some of this overtone work had been done, but I'll review some of that right here. So overtones, as I mentioned, are an infinite ladder of modes for any given angular harmonic, a given Lm. They are ordered by this n that means that higher n has lower damping rate, so they decay faster. And so the fundamental mode, so you see the overtones represented here in frequency, damping time, and the quality factor. Each color is a different tone, and it's a function of the spin. And you see the fundamental mode is always the longest lived mode, and the next first overtone is the second longest lived mode, and so on. Their frequencies are quite similar. In fact, they tend to be lower the higher end you go by a little bit, and you have the damping rates here. The higher tones decay way faster and have a lower damping, a lower Q. So These are all legitimate solutions to the Tucholsky equations, which are what discuss the perturbation theory in a curved space-time. And people had been, for a long time, getting to the fact that these are important in the description of the waveforms that kind of out of numerical relativity. So there had been a lot of work going back to maybe in 2007 in trying to extract those from the simulations. So not just the longest mode, but the faster decay ones. And so people have been using models with 2 overtones, 1 overtone, 3 overtones. And this number means the fundamental plus 2 and the fundamental plus 1 and so on. But it wasn't really, I think it's fair to say, until this work by Gisler et al. In 2019, where it was pointed out that really the full waveform, essentially from the peak onwards, is perfectly described by this spectrum of modes, as defined by the final black hole that comes from numerical relativity, final for us being the end of the numerical relativity simulation. And so you can grab the spectrum, you know the mass and the spin, you can predict what the quasi-normal modes are that correspond to that, and you can find that the whole waveform is perfectly described essentially from the peak onwards as a superposition of up to 7 overtones plus the fundamental mode. Of course, these overtones are doing all the work near this peak where the nonlinearities were expected to live, and they decay very rapidly. And so this is a log plot of the amplitude of the overtone as a function of time away from the peak. And you see later on, the signals dominated by the fundamental mode. Earlier on, the earlier you go, the more of these tones that you have to factor in. So this was an empirical finding in a way. It was not just that the signal was well described by the overtones, which maybe is not surprising. You can describe many things as a superposition of damped sinusoids, but also the fact that describing the signal in such a way allowed you to measure the random mass and the spin from the peak onwards very early on. So you can decompose fit the signal as a superposition of 7 overtones at the peak and have the mass and the spin as free parameters, and you'll recover the truth with high likelihood, the truth as it's known from the numerical relativity simulation. If you try to do that with just the fundamental mode at the peak, that's a very bad model and you get something that's totally off, which is not that surprising. Even more so, if you perturb away the frequencies of the overtones from the Kerr value, if you leave the fundamental mode alone as a function of mass and spin and perturb the overtones and try to do the same experiment, this breaks. So this sort of—
Quick question.
Yep.
So from the, it looks like just the fundamental plus the first overtone, because the rest of them are pretty close. Wouldn't that be enough? I mean, in terms of recovery, I was just curious.
Yeah. So in
Okay.
practice, given this, I'll show you in a little bit. In practice, for the signals we have now, that's enough.
Okay.
So the measurements we have done, we have two tones, 0 and 1. Or in the numerical, when you have the pure numerical relativity simulation, you need to add more.
Obviously, they
Yeah.
are.
So these studies essentially showed us that originally they were only with spin-aligned waveforms, so the progenitors were aligned in spin, although later on this was, there have been more recent studies that look at arbitrary spin alignments, and more or less it's the same with some caveats. The point is that for these waveforms, the whole waveform is perfectly described as a superposition of modes of the final black hole very early on at the peak strain. There's no sign that there's wild nonlinearities as was expected before. The amplitudes are recovered self-consistently in time, so you can analyze the signal at different points, recover the amplitudes, and they have the decay that you expect them to have, which is reassuring, at least for these modes, and numerical precision gets in the way, but anyway. And overtones contribute in some physical way, because if you perturb those frequencies away, then you lose your ability to measure the mass and the spin that you know from the simulation to be true. So these empirical claims are all we need to then go to the data and check whether that's the case. And of course, this is related to what you were saying, because the fact is where we look in the data and the kind of analysis we do, it's also relying on these facts that we know to be true in numerical relativity simulations that assume GR. And so it's not just a pure ideal Kerr black hole. Anyhow, so based on that, we can show that we can simulate a signal with the fundamental, and in this case, a second overtone if the signal is the same as in, if the signal is actually a Kerr black hole, we can measure this delta F, delta tau parameters and return a measurement that's consistent with 0. For different SNRs, you get more precision if the ring is louder, obviously. If you perturb the frequency away and it's too low, you can measure that. And if it's too high, you can measure that as well. Do you have, yeah.
Yeah, sorry. How do I read this? What's the
This plot?
Yeah.
Yeah, so
And actually also, how do I read the one before 2 slides ago? Sorry.
that's my bad. Okay, so spin, remnant mass, the two parameters that should describe, the remnant is a final black hole in our lingo. This is effectively a measurement. The brighter region is the more likely value from the inference, based in this case, just the NR simulation. And we know the truth extracted independently from this NR spacetime. And that's marked by the crosshairs.
Oh, okay. Thank you.
Yeah, sorry, that's good that you stopped me there. So darker is worse, lighter is better. And this sort of plot you read similarly, except the parameters that you see are this perturbation away from Kerr in the first overtone frequency and in the first overtone damping rate. And these are, in this case, 90% credible regions of a simulated LIGO measurement, slightly different than what I showed you before. This is simulating Hanford and Livingston and actually doing the whole thing.
And just the ring down portion.
Yeah, so this is using the approach of like just jumping,
Box cut.
and so it doesn't matter really what thing you find out.
And when you say deviation, are you just adding on gross numerical factors, or is there some principled way of calculating deviation?
So we are parameterizing this empirically, and so we know what the frequencies and damping rates are as a function of mass and spin for Kerr. We add an additional parameter that allows the frequency to float away from that. Then you presumably would compare this to some principled way of computing what these delta S should be under different models of non-Kerr objects. Or it's a phenomenological enterprise at this point. We just want it to be consistent with 0. And then if it's not, we panic. Okay, so we can do that. And of course, we can at the same time measure the mass and the spin, the frequency deviation and the tau, the damping rate deviation. We can just assume the object is a Kerr object and a Kerr black hole, in which case we get this orange measurement here for the mass and the spin. And you'll see these characteristic bananas that are actually lines of constant frequency for the fundamental mode, which is what dominates the measurement of the mass and the spin. And then if you enhance your model, adding these deviation parameters, you get simultaneously constraints on those. This is all in a simulated signal. You can reconstruct the full signal in gray, and you can reconstruct the individual modes and make it up in color. And this is assuming a Kerr object. And if going beyond the Kerr object in your model, then you get broader uncertainties about the individual modes because you allow them more freedom.
So for the PET, do you use just L is equal to 2, but many overtones?
Yeah, in this case, it's a model that has 220 and 221. So this fundamental and the first overtone of the quadrupolar mode in this simulation that I did.
So would you expect that the higher overtones are excited more than something with more angular momentum?
Yeah, so the higher overtones, as it turns out, you can leave them out given the SNR of the signals that we're simulating, because although they are excited louder, they live for a very, very short time compared to these other two modes. And so if you had a little more SNR, you have to include the next overtone, the n equals 2, and so on. And so we have, in the paper, we have simulations as to
No, but the question was, what about other values of L and M?
Oh, well, those are themselves way weaker.
They are,
At least for this system, that it's a 15 and 14 like system. So we don't even include it. It's like a factor of 10 less. But in principle, we could add them in the simulated signal. I just didn't. You can add as many modes as you want. Your mission will just get more complicated in that sense. Is that answer your
you have a
question?
way of estimating sort of the error that you make in truncating in L versus the error that you make in truncating.
Yeah, you can. In the papers, we do that. So based on the mismatch that, if you assume a limited number of modes, you can compare against the full waveform, compare how well or badly they match, and translate that into a signal to noise ratio, which tells you when do you expect to actually be sensitive to this. and it's basically at SNR where 1514 had SNR in the ring down of at most like 13 or so, but from the peak on. And so it's way too low for any of these things to matter. Eventually, yes, and it's a problem. It will be a technical problem once we have hundreds of mode that come into play, how we actually do that smartly. Okay, so we did this for 1514 back in 2019. And so we took these insights and we looked at the signal started from the peak onwards. You see this kind of plot again, where you have now the mass and the spin. And these are 90% credible
This is still
regions.
the highest, loudest event, right? Is this still the loudest?
I think after this last catalog, it's no longer by a little bit. Yeah. So you see these measurements of the random mass and spin, assuming a Kerr object, analyzing just data from the peak onwards. If you just analyze it with a single damp sinusoid, which would correspond to the fundamental mode of the quadrupolar mode, then you get a measurement of the mass and the spin that is in disagreement with what we expect from the analysis of the full signal. So, when we analyze the full signal, we get an estimate for the initial masses and spins of the progenitors. We know how to map that into final state based on NR simulations, and we can get a projected measurement of what the remnant mass and spin should be. And that's what this gray contour is representing. This, on the other hand, the blue contour is just fitting a damp sinusoid, parameterizing its frequency and damping rate in terms of the Kerr remnant mass and spin, and seeing what measurement you get just from the ring down alone. If you use a measurement that just has a fundamental mode and you start from the peak, you get something that is in tension with the full measurement, because obviously we don't expect the single mode to be a good model at the peak so early on. If you add one overtone, that goes away. I know the measurements are consistent if you expect, if everything's working correctly, and that's the yellow contour. If you add a second overtone for 150914, your measurement gets a little broader and you don't gain much, and this has to do with the fact that it wasn't that loud, and so really you can't tell that if there's a third mode or not, and so it's not doing much.
It looks like you're actually doing work.
That has to do with the fact that you're introducing two more parameters that are not constrained, because you have the amplitudes and the phase of the new mode that you're introducing. So it's just not, yeah.
And given the SNR, right? So
Given these
SNR,
data, yeah. So we can inject in our simulations and repeat this and show that then you, at some point you need to add it and you constrain it and so on. So if you look at the amplitudes of these modes, and this is a similar kind of plot again, except you have the amplitude of the fundamental mode, the amplitude of the first overtone, and the amplitude of the second overtone. This is a corner plot you may have seen. So this is again 90% credible regions. If you measure it with a model that has the first overtone and the fundamental mode, you get this measurement for the amplitude of these two modes, which is constraining the first overtone away from zero, and the fundamental, both of them, away from zero. If you add the second mode, the second tone, the second overtone, the third mode, that's a purple measurement. And if you look at this panel where you have the amplitude of the first overtone and the second overtone, it can't really tell if it can put power in the second overtone or the first overtone. It just knows that they can't both be zero. That's excluded. So there has to be at least one mode. There could be more, but the measurement one doesn't tell you. And so from that point on, we just take the two-tone models, the one that has the fundamental mode and the first overtone, and we enhance it with these non-Kerr degrees of freedom. So first, what we can do is actually reconstruct the signal before we actually do the non-Kerr thing, and reconstruct the individual modes and make up the ring down as we can measure it. And so you see this is a reconstruction of the 150914 signal. That's a blue line. Then the orange line, excuse me. The orange line is the contribution of the fundamental mode. The green line is the first overtone, and we can see maybe like one cycle. We can enhance that model with the non-Kerr degrees of freedom for the first overtone, and we can let them free and let the data tell us what values it can take, and it can be constrained to 20% around zero at one signal. So it's a weak measurement, but it just shows that this sort of thing can be done, and these measurements will get better as time goes on. Now we went crazy with this and also flip the logic a little bit and try to use the same sort of techniques that we developed to truncate the ring, to truncate the data and isolate the ring down, to just isolate the previous part, this of the spiral. And that allows us to get independent estimates of the remnant mass and spin, which we can translate into an area measurement. And we can check if the measurement of the remnant area of the initial black hole areas. So from the spiral, we can get a measurement of the initial black hole masses and spins, which we can translate into an area, a total area, the sum of the two. And we can do the same for the ring nut, just using this quasi-normal mode parametrization and get a mass and a spin and compute an area that corresponds to that. And we can compare the two and check if indeed the final area is no less than the original area of the two black holes summed, which is what we expect from the area law. And this is a measurement that we get. And so there's two kinds, there's two curves here. In one case, we're comparing the spiral to the overtone measurement that I showed you earlier, which is the green one here. And what you see here is that it's a measurement on the fractional change in the total black hole area from before the merger to after the merger. Or we can do the same with just a little more conservative, going later in time and just use a model that just has the fundamental mode way after the peak at a point where the signal should be described by a single damp sinusoid. And in that case, you get the orange curve. They are roughly consistent to a few percent. With the orange curve, you get like 96, 95% instead of 97. Probability of breaking the area law in the sense that the area could have decreased, and that's given by this little tail here of probability.
Just a quick question. Can you tell us how you produce an area from the mass and spin? Are you using a kind of formula that holds in the Kerr spacetime? Yeah, we're just assuming that M and chi, the functional form in terms of mass and spin. So we really measure mass and spin, and we're comparing if the areas are that. Right, but how can such a formula be used in this context? This formula holds for Kerr, right? Yeah, so this is saying, this is not testing for it, whether the objects are Kerr or not. It's saying you start with two Kerr objects, you end up with a final Kerr object. Do the respective areas match what we expect for the area law? So it's testing what happened in the process, how much energy was radiated and so on. It's not testing for. Okay, so under the assumption that we've been talking about since the beginning, then you get this. Exactly. Yeah.
But this is also fundamentally limited by the SNR, right?
Yeah, everything we do, this is really just should go away as we have more SNR. Eventually they'll get better. This is not that good of a measurement.
It looks like you're not violating the area law, but you're pushed up, interestingly pushed close to it. And that means not very much energy is being radiated.
So there's a limit as to how high this can be also, which is actually 3. This fractional change can't be greater than 3 due to conservation of energy. So there's two things. There's the area law, which tells you this can be too low, and this also conservation of energy that you can work out. It gives you an upper limit. So it has to live somewhere in between these two. And our measurement is just not good enough to rule this out.
What fraction of the energy is going out in gravitational wave?
It's like 10%. No, it's 3 solar masses out of 70 of the total binary.
I see. So that's a small number. Is that the same as this other small number?
Sorry.
Would you know in advance why? I mean, you might expect if you throw 2 black holes together, it's a pretty violent process. That amount of energy of order 1 gets radiated away. Whoa, wait, maybe that can't happen.
Yeah, so
what is the explanation for why that's so close to violating area law? Is that obvious or something?
I mean, it's not obvious to me because it has to do with the different models that are parameterized in the initial part and the final part, and how those measurements overlap and what little space you leave for the final mass and spin to be such that the measurement lives here. And the measurement from the ring down comes from a parametrization that's totally different from the spiral. And so it's not obvious to me why it's here rivaling up against 0 instead of rivaling up against 3. I'm not. I don't have an intuition, at least right now. Maybe that's something we should play around with. But right, so the measurement from the ring down just comes from the parametrization that it's an explicitly Kerr parametrization, whereas for the spiral we're using the NR surrogate of what we were using before. So it has to do with the systematics of the two. What kind of maybe I'm going to show you an additional plot. So this really comes from trying to oh shoot, you can't see this, can you? Trying to measure the remnant mass and spin from the ring down, which is the orange or the green measurements, or projecting it just from the measurement of the spiral, and you get this other measurement. And the way that these two regions overlap or don't is what gives you the plot that I was showing. And it's not obvious to me how that works out. I understand how the ring down measurement works out in the spiral one. It's not that clear. Okay.
Is this kind of offset seen for other events as well?
I don't know, because I haven't done it for other events. Okay. So this we understand very well, because as I mentioned, it's dominated by lines of constant, contour lines of constant frequency of the fundamental mode, which are dominating this. So that's the banana, but the blue measurement is the one that needs more poking at. Okay. All right, we're reaching the end. I wanted to show you, well, I don't have much to show you. But of course, 15 and 14 is not the only signal we have seen. We have many, many more binary black holes. The third LIGO Virgo transient catalog was just released. Unfortunately, the testing GR companion to that paper has not come out. So I can show you the one from the previous catalog, the second catalog, which is almost the same anyway, I can say without breaking too many rules. And so this sort of experiment was repeated for a number of binary black holes that had the right signal to noise ratio in the ring down. This is a constraint on the masses of the objects. Here's a representation of a number of them that were the better ones. And I should say this is done by an independent team. And so they're like basically independently replicating some of what we had found before. So you can analyze a number of these detections and you can combine them all together and get a good constraint, well, a better constraint on this delta frequency parameter. The deviation is away from Kerr, 0.04 plus minus 3 or so from the second LIGO Virgo catalog. That's from the kind of measurement I have been talking about. Then we have also been doing the first kind of measurement where you actually take the whole signal and enhance it in the ring down alone and measure these deviation parameters with the full waveform. If you recall at the beginning, I mentioned the second way of doing things. And in that case, you're measuring a parameter that we call delta F2 to 0 and delta tau 2 to 0 because you're allowing deformations in the fundamental mode, not the first overtone. And you can do that because you are comparing the ring down to also the spiral. And so you don't need to identify two modes independently to measure this parameter. And so these parameters are telling you something slightly different than those. It's a consistency between the whole waveform and the ring down part, as well as the different modes in this waveform mode. Anyway, long story short, the different models seem to so far agree with Kerr. You know, there are some potential systematics here. We don't know exactly why this is like that. But again, this kind of measurement is trickier because if you're playing with the attachment of the ring down to the spiral, so it's not really that surprising maybe, but we see that. The results for the new catalog are coming out soon. So stay tuned, I guess, hopefully like next week or so.
You told us you don't need to stay tuned.
You know. Anyhow, so since my time's up, I hope I've convinced you that black hole spectroscopy can give us a particularly clean way to learn about these spacetimes, whether you want to call it a test of no-hair theorem or whatever, all of these assumptions of our understanding of how these binary black hole coalescences should happen in vacuum and so on. This is a particularly clean portion of the signal to try to play around and do these tests on. They were enabled, these tests, by recent insights into the data analysis methodology and the theory. And there's still many open questions about how this all works out and what it tells us about the dynamics of these space coalescences in GR. But all these new facts have revitalized the program and have brought it to the attention of many of us that are working hard to understand better what's going on and what we'll be able to do in the future. In the future, of course, we'll have third generation detectors and LISA, which will be seeing hundreds of these modes. So we have a lot of work to do to get ready for that and understand what it actually is teaching us in terms of the theoretical implications of these measurements. So I'm excited and I hope you're too. I'm happy to answer questions if we have time.
More questions? Yes.
That's a good question. So these are very interesting variants of algorithms to analyze the LIGO data. And LIGO is, in my view, very much an algorithmically driven project. You know, I mean, you can look at these data different ways and you get insights, as you said. Is there general agreement from the algorithmic point of view on what needs to be done to the instrument now? Do all the algorithms want the same thing from the instrument, like longer baselines, orthogonal baselines, multiple points on the globe? Or is there some difference emerging in these different algorithms, like some higher signal to noise ratio for one site, or is there agreement on what to do next?
So when it comes to ringdowns, we basically want what everyone else wants. But in general, there's definitely different tensions as to what the measurement would demand. It's not just a specific algorithm, but the scientific target, or what part of the signal you want to target and see more clearly. So, you know, you could imagine if you want to see the ringdown very clearly, you could detune the detectors so that you get way better sensitivities at the kind of frequency that you expect to see this ringdown at for this kind of black hole masses at the expense of lower frequencies or higher frequencies or whatever. In terms of where to place the detectors, if you're doing a stochastic background search, you would benefit a lot from having several detectors in the same location, you know, if you're looking for the cosmological background. But that's not what you want at all if you want to localize individual sources in the sky. In practice, the science is really driven by multi-messenger astronomy and these binary black holes. And so even though there's some small like so far not focused science that you could do better with different configurations, I don't think it's ever considered seriously. So it's, you know, we really want to be able to localize a binary neutron star perfectly, and if on top of that you can do other cool things, fine, but they're not going to sacrifice that to measure the ringdown a little better. Maybe in the future, when we have many more, that we get many more detectors, we get more room to play around with these things. But so far, yeah. Does that answer your question?
Yeah.
Hey, first of all, great talk. It was really clear. And you mentioned all the way at the end that with Lisa you want to do some other things as well, right? Third generation detectors, obviously. But maybe a naive question, but with Lisa we're seeing some completely different parts of the spiral, right? So how do you go about learning if you're not looking at ring down? Can you use similar techniques as you described, or do you really need to couple Lisa to graph-based?
So for the purpose of this talk, with Lisa, you want the kind of sources that for which you would see the merger. And so these are not the usual, they're not binary white dwarfs, and they're not, so they are could be an emery or it could be something like that. And, you know, we have to hope that the rates are high enough that we do see those sources for the purpose of this talk. Of course, there's a lot more science you could do. You could see the spiral with Lisa alone and measure the parameters there. And if you do see it in LIGO later on, a year later, you can do multi-banding and do a ringdom measurement in the Cosmic Explorer band and compare that. And there'll be fun things to do.
Would that be helpful if you do like the frequency and you've seen it already in Lisa? Would that be helpful in determining the overtones, for example? Well,
it would be helpful in the sense that you're seeing the system very early on, and based on that, you should be able to predict exactly what ringdown we should see. And it's sort of magnifying this sort of consistency test that we can do now, looking at the early part of the signal, the later part, but like way better and with a lot more precision, obviously, because the signals will have a lot of SNR. And that will bring a lot of technical challenges because we can barely do that now with like 3 modes. And so we'll need to be clever about how we do it once we have hundreds and so on.
Could you explain why the relative change in area was kept at 3? Is it naively, if I have 2 black holes hurtling towards each other, it seems like it should be no upper bound?
You can't radiate more energy than you had originally. There's some limit coming from that. It's just you can have negative energy. Yeah. And so the fractional deviation, when I worked it out, it was like 3. Can't reproduce it. No.
But if I have two black holes of mass m, and then I set it up so they're hurtling towards each other with energy 1 million times m,
Or just 2 protons.
Yeah. And there's also ways to start with 2 particles and have no.
Oh,
horizon
well, but
and then get a horizon.
we know the initial state, right?
Okay, so it's based on some assumption about the initial state of some like stable orbit.
Yeah, this is a quasi-circular merger and so on.
Okay.
I'll dig out the paper and show it to you afterwards.
We have a last question from Camille Carlisle. She's asking, what would you need data-wise to say with reasonable confidence that you verified care or found something that violates it?
Well, disproving, like, we'll never be able to say, this is care with certainty. We can only say if we see a deviation, right? This is like a philosophical point. So no matter how much precision we have, there could always be a deviation that's slightly beyond that. So all we can do is just keep constraining these measurements to be tighter and tighter and tighter and tighter. And at some point, they will start ruling out specific models that predict deviations that are above our threshold. So, if you had a theory that predicted the overtone should have been different than 20% in frequency, we can rule that out already at 1 sigma, for example, for this specific binary black hole. Of course, you have to keep doing it for all, it is conceivable that there's a mixed population out there of objects that are Kerr black holes and some objects that are not. So you can't just analyze one single signal and call it quits. You want to keep doing it and keep combining these results in a smart way to try to see if all these objects are really Kerr or not. And I'll have a job forever. That's the conclusion.
All right. If there are no more questions, let's thank our speaker again.